Welcome back to our next discussion in the section on arc length, where we're going to continue on, finish up arc length with our formula that we developed in the first discussion, our examples in the second one, and we continue now and finish up this section by talking about taking that arc length now and revolving it about some sort of axis of rotation and generating a surface area. Because of the complexity of these problems and our lack of integration techniques, we are kind of limited in the types of things we can do at this point again, but we will look at some examples in which we can answer. And so we will restrict ourselves in dealing with surface area by, for right now, only revolving around the X or Y axis. Remember when we did volume, we can revolve around any sort of horizontal or vertical line we wanted. We talked about that. But in this discussion, we're only going to look at two situations, taking a arc and revolving around the x-axis, generating maybe a shape that looks something like this, or taking an arc and revolving it about the y-axis, generating a shape like this. And we're going to get a formula and a way to calculate these surface areas. Before we get into it though, I will remind us of our arc length formula, but I'm going to speak of it in terms of now a function. We're going to see why we're going to need this in a second. And so now I'm going to think of arc length as a function where I have some sort of curve in the plane. I call it f of t. I'm using the t variable here instead of x. Remember, it's just a letter used to represent an unknown quantity. Doesn't matter that it's t or x. And I'm saving x because I'm using x as a different variable in this case. And so I have a curve f of t in the plane. I have some anchor point A in which I will start out a measurement. And starting at A, I will measure the length of this curve starting at A and ending at, well, x, being some unknown variable. I'm choosing to move away from A a certain amount to some x value, and that would then generate the length of this curve up to x. And then I can measure the length of the red curve, the red part of the arc. How would I measure that? Well, it would be the arc length formula starting at A and ending at x. So this is a function of the x variable. It's the arc length up until x, starting at A. What's the arc length formula? Remember, it's the square root of 1 plus the derivative of this curve squared, dt, right? T is my variable for the function, so that's kind of there. We're going to need this version of the formula because what we're going to see when we develop surface area is I'm going to need to measure a differential, a derivative of arc length. And in doing so, I'm going to need to think of arc length as a function in order to take its derivative. All right. And so with that being said, let's begin our discussion in talking about surface area. Now remember, it's not volume. We're revolving a one-dimensional object, a curve in space. And so when I revolve a one-dimensional object or a curve in space, I do not generate a solid. I generate just a surface, something hollow, right? There's nothing inside of this. I can stick my hand through it. It's a piece of paper that's wrapped in a certain way, or that's molded in a certain way. There's nothing inside of this shape. It's hollow. So it is just a surface and therefore only has area. There is no volume to calculate, just the area of the surface we've taken up in three-dimensional space. Likewise here, right, if we revolve around the y-axis. And so I'm going to use the same principles that we learned in the beginning of chapter 7 when we calculated area and volume. And instead of trying to figure out the surface area of this entire object, let's think of it at an infinitesimal level. Let's take a single x value between A and B, look at the point on the curve here, a cross section at that point, which is now just a single dot, and I'll revolve only that cross section of the arc, or only that single dot. In this case, it doesn't generate a circle, a solid circle, but it generates a circle, but just the circumference of that circle. And so if we look at the circumference of these circles, the circumference of the circle would just be 2 pi r, right? That's the circumference of a circle in general. Now in this case, we're looking at x and y axis rotation, so the circumference of the circle explicitly would be 2 pi f of x, 2 pi r. F of x is the distance between the x-axis and the curve, distance between the center and the edge. The edge is on the curve f of x. So the radius of these circumferences is f of x in general, depending on where I'm at between A and B. Let's go over here. What would the circumference be here? Remember, we're only revolving a dot instead of the entire curve. If I revolve a dot, I get a circumference of a circle. In this case, we would need to know the distance from the center, which is at 0, to the edge, which is in this case just at x. right? We need the distance from the center to here, which is just whatever x is, x minus 0. And so when we revolve around the y-axis, the radius is actually just 2 pi x. And then we have the discussion, okay, well, now that I know the circumference of a single circle, we would just need to add up all of these circumferences. And so we can begin to generate, I'll use SA for surface area, an integral that's going to develop or generate this entire surface for me, just like we did with volume. I'm going to add up the circumferences of these circles, starting at A and ending at B. But what we're going to need to do is that we're going to have a problem here. Usually there goes a dx. And we're going to see why we can't have a dx here in a second. I'm going to write the other one as well. Kind of get a start to our definite integral, 2 pi x. And again, we'd like to throw a dx here, right, as we move continuously along the x-axis. Unfortunately, we can't do that. Remember, anytime we do a definite integral, we need to always equally space things out. Right? Equally partition the x-axis, a delta x fixed distance. That way, as we throw more and more rectangles in, or more and more cross-sections in, they're all equally spaced out. And as I put more and more and get to infinity, we have no issue of some getting grouped up faster than other ones. We need everything equally spaced. That's always the important thing about delta x, a fixed distance delta x, a base to our rectangles. And then delta x goes to 0 evenly. We have an even spacing. Unfortunately, though, if we partition up points evenly along the x-axis, we will not necessarily get even points along this curve. So if I partition the x-axis up evenly, we're not guaranteed that these points on the curve are equally spaced out. We can think of a very simple example here. I'll do it under here. We do a really sharp curve like this. And say we have 3 points here that are equally spaced on the x-axis. So if we look in the x direction, the points are equally spaced. However, if we look at the difference between these dots on the curve, they are not equally spaced. We have never run into this problem before, and you can go back and look at the other previous lectures and videos in which we partitioned up the x-axis, and we never worried about it because I guarantee if you look back, if we partition up the x-axis evenly, all of my cross-sections, all of my straight lines were still then evenly spaced out because my cross-sections or my straight lines, they were all vertical x lines. And so if I partition x up evenly, it partitioned those lines up evenly. If I partition x up evenly here, it does not partition these dots up evenly. Now, if I want to make sure that when we revolve this about the x or y axis, and we put more and more circles to add up, or eventually infinitely many of them for all x, I need to make sure everything's evenly spaced out. And so for that reason, we need to put something else here. For a brief moment, I'm going to write something that's incorrect. I'm going to put ds. Not that it's incorrect, but it just is mixed variables here, so we don't like it. And ds. Where ds represents an even spacing along the curve, guaranteeing me that, okay, I will first evenly space out points on the curve, and then figure out what that would lead me to a spacing along the x-axis. If I evenly space out the points on the curve, how does that translate to the x-axis? So I will move evenly along the curve, ds. Remember, s is the variable we use for the curve. Now, we don't like this because we have x in one variable, s in the other one, same thing here. And so we can't use this formula right now as it's written, and that's why I wrote this function up here. Because in generating surface area, I need a ds. I need the derivative or the differential of arc length. Well, fortunately here I have written arc length as a function. And so that means all we need to do is take the derivative of this function, ds dx. And the nice thing here is all we need is the second fundamental theorem of calculus. We are taking the derivative of a definite integral, and therefore we have some sort of relationship, right? That's the beauty of the fundamental theorem of calculus. And if you look back in Calc 1, when you learn the second fundamental theorem, this is a very easy answer to get. It is verbatim the second fundamental theorem of calculus with this specific function would then give me this. F prime of x squared. We get just what's inside, just in terms of the variable x. This is the second fundamental theorem of calculus, gives me this. And then remember, we want ds, or the differential, so all I'm going to do is move that dx to the other side. And now we have a relationship between an even spacing on the arc to an even spacing on the x-axis, and this is the relationship between them. And it's an arc length relationship, right? That arc length formula that we saw. And so now going back over here, what we can do is we can replace that ds with something in terms of dx, where now it makes everything nice and cohesive and in terms of the same variable. And what do we need to attach? The following. There we go. And the same thing here. And so here are our formulas for surface area when I revolve around the x or the y-axis. And if you look at the integral as a whole, it is not as complicated as it may look, because just remember, we're adding up circumferences of circles, 2 pi r, where the radius here is the function, the radius here is x. The only problem is we need to partition up the arc length evenly, and that would require this to be thrown in. So it's the circumferences of the circles as I move along the arc, the circumferences of the circles as I move along the arc, and we're adding all those up. So it's the same principle or ideas that we learned at the beginning of chapter 7. It's just a slightly more complicated integral. And so these are the two formulas we will use. And so in this video, we developed the formulas for arc length and surface area, we used the formula for arc length to get the formula for surface area. And in the next video, in the next discussion, what we'll do is we'll take these formulas that we've developed and put them into practice. So we'll look at some examples of calculating surface area and answer some integrals that at this point we can solve. All right, so I'll talk to you guys soon.